In this video, we are going to continue our discussion of radioactivity from Chapter 8. Just to remind you, radioactivity is the spontaneous breaking up of unstable nuclei with the emission of one or more types of radiation. So we're focused on the nucleus here. There are three types of radiation: alpha, beta, and gamma. We have already discussed alpha, so now we will move on to beta. Beta particles are formed when a neutron disintegrates, producing one proton and one electron. The proton can remain in the nucleus, but the electron is emitted. This electron that's emitted is our beta particle. So our properties: it's negatively charged because it's comprised of one electron. It's emitted from the atom in a fast-moving stream, so it's faster moving than alpha particles. It's also more penetrative than alpha particles, and in order to stop it, you would need 2 to 3 millimeters of aluminium, as opposed to the few sheets of paper or the skin that would block alpha particles. Carbon-14 is an example of a beta emitter. It's used to age deceased living things. You might have heard of carbon dating in history before. Carbon-14 decays according to this equation. So we are producing an electron and the proton number, or the atomic number, is increasing by 1. You can see again here that the change in that atomic number means that a new element is formed. If we look at gold, we can see that a new element is formed as well. We are producing an electron, our beta particle, and the only thing that changes with regards to our values here is that the atomic number increases by 1. If you look at your periodic table, the element with an atomic number of 80 is mercury, and this is the symbol for mercury, Hg. Beta particles, to sum them up, are electrons with a negative charge. They're faster moving and have a greater penetrating ability than alpha particles. And here is a general equation for beta decay. Gamma radiation consists of rays, not particles. So it's electromagnetic radiation released from the nucleus in order to lose surplus energy that is built up in there. Because it is a ray and not a particle, gamma rays have no mass or charge. This allows them to travel very quickly at the speed of light and have greater penetration than alpha or beta radiation. In order to stop them, you would require thick shields of concrete or lead. If they're absorbed in large quantities, gamma radiation can change the structure of cells of living things. Now, usually this is a bad thing, but it also has beneficial effects as it is used to treat cancer. This radiation can be focused on the cancerous cells, changing their structure and destroying them. The gamma emitter that is used in the treatment of cancer and for some food irradiation is cobalt-60. And you can see by the equation here that there's no new substance formed, there's no change to the substance, but we are releasing energy. Energy is produced. To sum up our gamma rays, they are high energy electromagnetic radiation with greater penetrating ability than alpha or beta particles. So they're faster moving and have greater penetrating ability. It might be good to note here that no new substance is formed. No new element is formed. We're simply producing energy. It's important to be able to make a distinction between nuclear and chemical reactions. We have looked at a lot of chemical reactions so far in Leaving Cert Chemistry. And what we have seen in them is that no new element is formed. We may rearrange our elements and have bond breaking and bond forming occurring, but no new elements are formed because there's no change to the atomic number. There's no change to the number of protons in the nucleus. Nuclear reactions, however, a new element may be formed. Any change that's occurring is occurring in the nucleus, And for that reason, there's no change to any bonds. There's no bond breaking or bond forming. Nuclear reaction is a process that alters the composition or structure or energy of an atomic nucleus. When we're talking about composition or structure of the nucleus, we are talking about alpha and beta particles. When we're talking about the change of energy in the nucleus, we're talking about gamma particles. A radioisotope is a radioactive isotope. Not all of our elements on the periodic table are radioactive, but they all do have isotopes, and some of those isotopes may be radioactive. A good example of this is that carbon that we discussed before. Carbon-12 is the most abundant carbon isotope. That is not radioactive, which is brilliant because it's present in so many different things around us. Carbon-14, the carbon-14 isotope is radioactive. We mentioned that earlier in the aging of deceased living things. The half-life of a radioactive isotope is the time taken for half of the nuclei in a sample of the isotope to decay. So let's discuss what that means. If I take a sample of isotopes, let's put 12 isotopes in here. The half-life is the time it would take for half of those isotopes to decay. So I had 12, so the half-life is the time it would take for 6 of them to decay. Now, let's say that took 1 day. 1 day. The next half-life would be the length of time it would take for half of the isotopes left here to decay. So it would take 1 day again for that to happen. And 1 day later, I would have the ones that have decayed, and half of my sample that's remaining would have decayed as well. So it's the time taken for half of the isotopes in the sample to decay. So the emission of radiation is an entirely random process, and we can measure it using a Geiger-Müller tube and a rate meter. The half-lives of different isotopes vary greatly. Carbon-14 has a half-life of 5,700 years, cobalt-60, 5 years, and polonium is just a fraction of a second. So you can tell polonium there is much more radioactive, much more unstable than the others. Looking at our detection system, our GM tube, our Geiger-Müller tube, is connected to a rate meter. So this is the GM tube. And what we do is we point that, we bring that in close proximity to our substance that we're testing. So that's the black substance down here. And we connect it up to a piece of apparatus called a rate meter. The rate meter measures the number of radioactive particles entering the tube every second. And it will produce a graph for us to show how many particles are being produced per second. That is how many alpha, beta particles are being produced, or gamma rays. Cesium-137 has a half-life of 30 days. What fraction will be left after 90 days? So in the first 30 days, we're going to lose half of them. So we will only have half of our isotopes left. In the next 30 days, we will lose half of that half. So we will have a quarter left. And in the final 30 days, so on day 90, we will have a half of that quarter left. So we will only have 1/8 of the original amount of isotopes left. If we take that example over here, and if we say we had 100 to start with, after the first 30 days, we would have half of the 100. So that would be 50. After the next 30 days, we would have half of the 50 would have been decayed. So that would be 25. And on day 90, we would have half of the 25. Now, I've just plucked a random number there using the 100. Obviously, you can't have half an isotope, but hopefully you're seeing where I'm going with this. So it's important to work it out that way. If you were given 100, you can't say that, okay, half of 100 is 50. So 50 of them will be gone after the first 30 days. And then after the next 30 days, another 50 will be gone. So there'll be 0 left. We don't do it that way. You have to work it out that however many you have left, half of those will be gone in the half-life. However many you have left here, half of those will be gone in the next half-life. Radioisotopes have many uses. One we mentioned already was in the treatment of cancer. Cobalt-60 produces gamma rays which, when controlled and carefully administered, can destroy cancerous tissue. Gamma radiation is also used in medicine to sterilize instruments by destroying bacterial cells and germs. Another use of radioisotopes is in archaeology, where the carbon-14 isotope, which emits beta particles, can be used to estimate the age of artifacts. A common exam paper question is asking you to outline how this works. You need to mention that when things are living, the ratio between carbon-12 and carbon-14 is constant. However, after death, the unstable carbon-14 isotopes will decay, while the stable carbon-12 isotopes remain unchanged. They won't decay. Measuring the ratio of the carbon-12 to carbon-14 isotopes and using the value of the half-life of carbon-14 can be used to age the object. Other uses of radioisotopes include in agriculture, where scientists study things like the uptake of fertilizers by plants. Food irradiation, where food is preserved using gamma rays. And in industry, where leaks from underground pipes can be located without having to dig up the entire pipe by adding radioisotopes to the substance in the pipes. And where those radioisotopes are then detected, that's where you know your leak is.